Good morning everybody, and welcome to our second webinar on the Low Carbon Networks funded project called Respond. My name is Paul Marshall and I am the Respond Project Manager. Thank you for registering to take part in our webinar today. Our audience is a broad spectrum of industry participants representing network operators, energy suppliers, equipment suppliers and end consumers. I do hope this webinar has something of interest for all of you. A quick look at the agenda for today. Firstly, I'm going to provide some background to the Respond project. Then an overview on our project today, what we're up to. A review of Respond techniques and where we're up to in the trials and analysis phase. And touch on the customer aspect of the project and then the next steps. Then at the end of the presentation there will be an opportunity to put questions to me and other members of the Respond team. The format of the webinar includes a presentation which will take around 25 to 30 minutes, followed by a question and answer session of around 20 minutes. Can you please submit your questions online during the webinar using the box on screen? As well as feedback on the project itself, we are all interested to hear your comments on the webinar technology. So we'd be grateful if you could complete the short survey at the end of the webinar by clicking on the survey button at the bottom of the screen after the Q&A session. The Q&A panel at the end of the session will be myself, Paul Marshall, Project Manager. We have Paul Turner, who is our Innovation Delivery Manager. We have Steve Stott, who's been a Technical Workstream Lead on the project. And we have Tracy Kenley, who has been the Innovation Customer Delivery Lead. At Electricity North West, we are leading the way in developing smart solutions to meet the UK's future energy challenges. This means accelerating change where demand and generation will grow, placing stress on the network both in normal operation and during fault situations. Our previous projects have looked at how we manage the network during normal operations. However, the Respond project looks at alternative ways of managing our network after the unexpected by delivering an intelligent approach to managing fault level. So what is fault level? Our network is designed to handle normal current 24 hours, 365 days a year, and is protected by circuit breakers and other devices at key locations. When a fault occurs on the network, fault current surges towards the point of the fault from all sources of generation. This fault current is much greater than normal current and places stress on all electrical equipment it flows through. The protected devices react quickly, so the fault is disconnected from the sources of the generation. The amount of fault current that flows will vary depending on the type of fault, its location, and how the network is configured and the sources of generation present on that network. If unchecked, the fault current can damage equipment in a matter of seconds. The fault level is the maximum we expect this current to be, i.e. the maximum potential fault current. We know the maximum potential fault current changes during the day, as seen on the graph, as we change and configure the network and source of generation are switched on and off. Using our historic design models, we predict what the worst case fault level will be to ensure the network operates safely, taking into account the maximum rate at which the equipment can safely perform. When the potential fault current is larger than the rating of equipment, our approach has been to replace the equipment with a higher rated equivalent. This is reinforcement is expensive, time consuming and disruptive to customers. And this approach doesn't provide an accurate way of measuring fault level either. The question is, how can we work smarter, predict fault current more accurately and avoid resorting to expensive reinforcement? This leads us on nicely to Respond, which is the first UK demonstration of an active fault level management solution that avoids traditional reinforcement. It's a £5.5 million project which was competitively won through Ofgem's low carbon funding. The project started in January 2015 and is supported by several project partners as shown on the slide. These partners help us to maximise the benefit from the project. We have completed the design and installation phase of the project and we went live in May 2016. And we're now into the trials and analysis period of the project, which lasts 2 years. Project hypotheses What we're trying to intend to prove during the project are the following. It's faster and cheaper to apply than traditional reinforcement. It will deliver a by order of fault level mitigation solutions based on a cost-benefit analysis. It will facilitate active fault managers of fault current using retrofit technologies and commercial services. It will enable a market for the provision of a fault current limiting service. It will use existing assets with no detriment to their health. And at the end of the day, it will reduce bills for customers by reducing network reinforcement costs. When a fault level approaches or rises above the fault level rating of our network equipment, the fault level assessment tool, known as a FLAT, which is now embedded into our network management system, will enable or disable one of three innovative techniques designed to manage fault current. They are adaptive protection, the fault current limiting service, and the IS limiter. All three techniques, when enabled, respond after a fault, reducing fault current so that every item of network equipment operates safely. For the FLAT tool, fault level assessment tool, to operate correctly, we need an accurate and real-time network model. The network management electrical model is derived from our existing data, including geospatial, known as GIS system. And any real-time changes to the network configuration will be presented to the FLAT tool. The tool is designed to calculate fault level after a topology change, or periodically after 5 minutes, allowing near real-time modelling. This slide shows a screenshot of a small section of Atherton Town Centre network. At this site we've installed HV adaptive protection. I will go into this technique a little later. In the event of a topology or time trigger, the fault level assessment tool will carry out a fault calculation. If the fault of any device exceeds its design rating, the FLAT tool will issue an enable signal to the adaptive protection relay at the respective response site. If the fault level reduces, it will then send a disable signal to the device. If there is no signal or the communication fails, then the technique will automatically enable, like a dead man's handle. The topology trigger occurs when a state of any selected switch changes, causing the FLAT tool to perform calculation. This next slide is a screenshot showing the devices then highlighted in the yellow boxes which have exceeded their design rating. There are a number of different ways this information can be presented, and this is just one of them. This slide shows the layout of the Respond dashboard within our network management system. This is a control and monitoring screen purely for the Respond network. From the screen, it is easy to identify the operational status for each Respond network. The FLAT status column tells the user if the Respond site is on, off, or in test mode. It is possible to assign a unique profiler or the same profile to all substations. Our first technique I would like to talk about today is adaptive protection. This is also known as sequential tripping. As I mentioned before, our network is already designed to break fault current and isolate the fault section of a network using circuit breakers and other protective devices. Adaptive protection changes the order the circuit breaker operates to safely disconnect the fault from the rest of the network. Using the redundancy built into the network, we can ensure that no other customers will go off supply as part of this change. To provide some example, this is how our network works at the moment. Electricity is generated by power stations around the country connected to national grid. From here it flows down to local distribution network owners like Electricity North West. Electricity is then distributed to homes and businesses through a network of smaller substations, overhead lines and underground cables. Here you can see domestic and business customers on the right hand side of the diagram and a customer with a combined heat and power plant on the left hand side. Adaptive protection alters the sequence our network breakers operate. The red squiggly arrow on the right depicts a fault on our network. All protective devices start to operate, but the closest one to the fault operates first and disconnects customers of the network beyond the fault. In this example, the red circuit breaker would not normally operate first, removing the fault from the network. However, in this example, the red circuit breaker's fault level has been exceeded. So the flat tool could enable any other circuit breakers in yellow, so they will open quicker than the red circuit breaker, reducing the fault level on the network, so the red circuit breaker can operate safely beneath its fault rating. We have this technique successfully installed and working at 5 of our substations, and so far we have had 3 successful operations of adaptive protection. The IS limiter, this is our second technique. It is a current limiting fuse. Our standard equipment will normally identify a fault and respond to it within a couple of 100 milliseconds. This may seem fast, but the fault current will have already peaked within this time frame. An IS limiter will operate within 5 milliseconds or 1/200th of a second before the fault current reaches its peak. When enabled by the fault level assessment tool, the IS limiter will monitor normal current flowing through it. When a fault occurs, the IS limiter detects the rapid rising current and responds by setting off a small explosive charge which breaks the normal flow of current. Removes some of this fault current flowing through our at-risk asset equipment and allows it to operate safely. IS limiters are in use on private networks in the UK and public networks worldwide. However, they're not used in UK public networks. As well as proving the effectiveness of this technology, Respond will review the safety case and the use of these devices on UK networks. As part of this project, we have effectively replaced existing circuit breakers with IS limiters at 2 locations on our network. We have 2 sites where we are trialling the IS limiter. The first is at Bamber Bridge in Preston. At this site we have the substation busbar section open, and the IS limiter is acting as a closed busbar section breaker. If the fault level is exceeded for any of the circuit breakers at the substation, the flat tool will enable the IS limiter. If a fault then occurs, the IS limiter will operate in 5 milliseconds and effectively open the busbar section at the substation, which halves the fault level of the circuit breakers will see, therefore operating safely. The second site is at Broadheath in Manchester, where we're using the IS limiter in a different configuration. At this site we have the IS limiter acting as a closed transformer breaker. The green line and the blue arrow at the right of the slide are just a bypass switch used during the trial and would not normally be installed. If the fault level is exceeded for any of the circuit breakers at this substation, the fault level assessment tool would enable the IS limiter. As before, if a fault then occurs, the IS limiter will operate in 5 milliseconds and effectively open the breaker at the substation, which reduces the fault level of any circuit breaker we'll see, therefore operating safely. As an example, these are external photographs of the 2 IS limiters. The one on the left is at Bamber Bridge, and the one at the right is at Broadheath. Broadheath, as you can see, has 2 containers during the trial. The second container is to house the bypass circuit breakers. Inside these 2 containers, the photo on the left is the IS limiter, which is made up of 2 parts. The first and the far left is a circuit breaker controlling the IS limiter, which provides a 3-phase treat when any of the IS limiter fuses blow. Attached to that is the IS limiter, which is a horizontal withdrawable fuse on a carriage. The photo on the right is a bypass switchgear at Broadheath. IS sensing units. In order to trial the IS technology at more sites but at a reduced cost, we have utilised the IS sensing units at 5 sites. These units detect and operate after a fault exactly the same as an IS limiter, but without the actual cost of the IS limiter. This approach allows us to trial the effectiveness of the technology across a wider region. The photo on the left is an IS unit installed on our substations, and the photograph on the right is the IS sensing CTs installed at one of our substations. Part of the project is to understand what effect Respond has on our existing assets, as we operate them differently and more frequently than before. Therefore, we've installed a number of health monitoring techniques to see what effect Respond has on our assets, to see if we need to maintain or replace them differently than we currently do. The photo on the bottom left is a dissolved gas analysis device which will continually measure the condition of the transformer during the trial. The photo on the bottom right is a Kalman profiler which measures the electronic signature the circuit breaker makes during its operation. This can be compared to previous operations to determine the effect on the circuit breaker. The top photograph is an ultra-trev unit which will continually measure the acoustics and partial discharge of the circuit breakers. The third technique I'd like to go on to is the fault current limit and service. Fault current can be generated from a number of sources, including customer equipment running in synchronization with our network. The largest of these are rotating plants, either designed to generate electricity or large synchronous motors that usually consume electricity, but in a fault condition can easily flip into being a generator when the supply voltage drop. These rotating machines can supply up to 8 times their load current at the time of a fault. Fault current limit service enables us to disconnect the fault current generated by industrial, commercial and generation customers using new technology which will be trialled under the Respond project. This commercial solution will enable customers to earn rewards and will benefit all distribution customers through reduced reinforcement costs. We believe there is significant equipment out there that is contributing to fault current that can be part of the solution. Our challenge is to identify customers who have such equipment, engage with these customers to explain Respond and see if and how they can contribute. The fault current limit service could work like this. In this example, electricity flows through the 2 transformers to the factory on the left and the homes and businesses on the right. At the factory, different types of equipment are connected to the network, including a large motor and a generator. A fault occurs again in this red squiggly line on the right. The fault current rushes towards the point of the fault. All protective devices start to operate, but the closest one to the fault operates first, disconnects the customers on the network beyond that fault. If we can reduce the fault current to a lower, safe level before the circuit breaker operates, we won't need to upgrade any of the network equipment, which can be very expensive, or the customer may not have to pay an expensive connection charge. One way of reducing the current is to disconnect the customer's motor or generator. This could happen instantly using new technology deployed as part of Respond. Once the fault section has been isolated, the motor and generator can be switched back on. The rest of the customer's equipment would remain on as normal during this fault, as only the selected items of plant would be interrupted, and only until we have disconnected the fault, which could take up to 10 minutes. In this example, the red circuit breaker fault level has been exceeded, so the fault level assessment tool could enable any of the circuit breakers in yellow at the customer's premises to operate. They will operate quicker than the red circuit breaker, reducing the fault level in the network, so the red circuit breaker can operate safely beneath its fault rating. As part of the Respond project, we're trying to find out a few things. If the customers have equipment that can contribute to fault current, how big the equipment is and whereabouts it is. Are the customers willing for this equipment to be disconnected? If so, and when? What commercial and technical arrangements need to be in place to facilitate this? And ultimately, the project will identify long-term benefits of the fault current limit service to customers across Great Britain. The customer hypothesis we're aiming to prove is that the method enables a market for the provision of a fault current limit service. Customer engagement will enable us to take response to the market, optimise the proposition, and then trial the method. Firstly, we established an engaged customer panel made up of a cross-section of industrial and commercial customers to review, challenge and formulate the engagement customer material and the survey instrument. This approach enabled us to develop and deliver the customer survey to market. We then undertook the customer survey to test the appeal and establish the price point of this new commercial proposition. The final piece of research will be undertaking the fault current limit service trial participants to understand their experience of taking part in the trial. So how did we go about the customer survey? Electricity North West provided impact research on almost 1,700 records of industrial and commercial customers to support the recruitment of the survey. The data was screened to ensure the organisation met criteria to provide a fault current limit service, i.e. they owned a motor or operated generators. A suitable key individual was identified and a survey was sent to them, which was a total of 303. To support recruitment, we also used our project partners, ADE and Energy, to market the fault current limits and trial and attract customers to participate in the survey. This enabled the survey to be rolled out across Great Britain rather than just in E&W's area. A total of 103 industrial and commercial demand and generation customers across GB participated in the customer survey during October 2015 and February 2016. The purpose of the customer survey was broadly similar to the approach adopted by E&W's previous commercial projects, C2C, capacity to customers. The first section of the survey gathered some background data on each of the survey participants, such as their industrial classification, to help us do analysis on the market sector. Details of the largest AC rotating machine and the largest combination of rotating plant, and also the implications of their equipment being constrained for up to 10 minutes. In the second section, we introduced the fault current limit service concept by using a range of communication materials developed in the ECP, a video, a water analogy to illustrate fault current, frequently asked questions, and a high-level concept board. Then we tested the perceptions, the appeal, the likelihood to consider the take-up of the fault current limit service, the drivers and the barriers to participants. In the final part of the survey, participants were asked to complete a state of preference exercise, where customers were asked to select a preferred option for a pair of possible fault current limits and contract scenarios. The result of this exercise helped us determine the optimum price point, payment method and contract length of the service. There is a separate slide deck on our website which provides a lot more detail on the customer survey, but for the purpose of today, I just want to share with you the highlights of the 103 customer surveys. 43% stated that it was essential that their business had electricity 24/7. 25% stated that 10-minute constraint on equipment would cause significant impact to their business. But 25%, equivalent to 25 customers, stated that a 10-minute constraint would cause no significant impact. These customers represent our target market. So the good news is that the survey provided the hypotheses that we were able to identify a market for the fault current limit service. The target market was identified from customers who are mostly from non-manufacturing industries and who are able to constrain their motor or generators without significant impact for up to 10 minutes. The project aim is to establish up to 5 of the fault current limit service contracts within the two-year trial period. The first 2 will be our project partners, United Utilities, at 2 of their sites, one with a large motor and one with a CHP unit. The next steps from today are that we have now successfully deployed the fault level assessment tool into our network management system. We have the adaptive protection and IS devices installed, and we're working into the trials analysis period for the next 2 years to see how these techniques work. We will be reviewing and examining the key questions for the project with the aim to answer them. We are now entering the customer recruitment phase for the fault current limit service. We are building the safety and reliability case for each of these techniques to be applied across the UK DNOs. And we will be producing a buy order and cost benefits for the various fault level mitigation techniques. The presentation is now complete, and I would like to introduce my colleagues who have been working on the project to answer your questions.
So the first question we've got then is, what do you think are the main barriers to customers taking part in the fault current limiting service?
Right, I'll take this one, Paul, thank you. So far that we're finding that it tends to be concerns about risk that are proving to be the greatest barriers from organisations transitioning from an expression of interest to actually entering discussions about a managed agreement. Therefore, it's not currently possible to evaluate industry confidence in the technologies that we propose deploying to facilitate the FCL service. The key areas of concern, and these were raised by both the Respond Engaged Customer Panel participants and the organisations that expressed an interest in the FCL service that took part in the survey, are a general nervousness around risk to equipment, some concerns about resilience to their business operations, and some general concerns about security of supply. Another concern that seems to be expressed about the FCL service generally is some nervousness about the number of times that customers' equipment could potentially be constrained under a managed agreement. Now, there are currently no fault level issues on our network, so for the purposes of the trial, it's very likely that we might have to artificially lower the protection settings on our customers' equipment circuit breaker to manufacture the conditions under which we would operate in business as usual in order to test the remote enabling technologies. So it's likely customers would only actually experience one interruption during the trial period.
Okay. Okay, so the next question is, what happens if one of the primary transformers is out for maintenance or fault?
Okay, well, I'll take that one, Paul. It's a very good question. There's a two-layer approach to this in Respond. The first layer really is on site, which is where the adaptive protection equipment is effectively interlocked with the breakers that supply the site. For example, if one of the primary transformers was out for a maintenance or fault, then the other primary transformer was in service and the bus section was in service, adaptive protection wouldn't work. So if any one of those three circuit breakers are open, adaptive protection is disabled locally on site. That's a hardwired thing. And in addition, the flat tool will be configured such that it wouldn't allow that condition to operate either. So there's like a dual lock there.
What type of fault level issues will Respond address?
Okay, in terms of Respond, we're only looking really at brake issues, so pretty much fault level issues go down into two different components, which is make and break. So make is when you're trying to close onto a fault, which is usually very large fault level issues, very large fault current issues. Respond doesn't deal with that at all. Even though we have IS limiters, which potentially could deal with that, that's not part of the remit of this project. So what we're really looking at is things happening about 90 milliseconds after the event. So break is the thing we're looking at, not make.
Okay, we've just got one more question at the moment. So. Are there any conflicts of existing services? And I presume this means the fault current limiting service. So,
Right, I think that's another one for me, Paul. Potentially. Of the 103 survey respondents, there were only 7 that had other commercial arrangements in place. Now, we do believe that these arrangements could potentially present a barrier to organisations considering providing a fault current response. This is one of the areas that we intend to investigate further to better understand the barriers to customers with existing arrangements in place with other industry players. Now, whilst it appears that there might be potential conflicts, equally there could be possible synergies which might be lucrative to some organisations. We're continuing to work with our project partners, Energy and the ADE. They have a much more direct relationship with their own customers and associate members, and that relationship will enable us to understand the barriers of the FCL service to customers operating in the store, electricity storage, DSR and capacity markets. However, so far it appears that issues concerning risks are the biggest barrier to considering taking up an FCL service managed agreement.
Okay, thank you, Tracy. Just have one more question coming in. So, have you found it difficult to engage with large industrial and commercial customers?
Yeah, we have actually, and this had been anticipated because of difficulties engaging with this particular market sector in previous projects. What we've learned from experience is that collaborating with our trusted partner organisations that have access to third parties can help us to find the right person to talk to within commercial organisations. So as such, as part of this project, we recruited the support of outside partners, the Association of Decentralised Energy, which was formerly the Combined Heat and Power Association. But despite this, it's still proven to be extremely difficult to engage with large demand and generation customers. Now, we do recognise that the time of their decision makers is extremely valuable. Our partners have so far assisted us, as Paul referred to earlier, in publicising the SCL service to enable us to recruit survey participants so that we could evaluate the appetite for the concept and the price points at which these customers appear to be interested. However, since the survey, it's proven to be extremely difficult to re-engage the survey participants that responded positively and expressed an interest in taking part in the trial. So we hope that our continued collaboration with our project partners will help us to secure just a small number of managed agreements with organisations that potentially are prepared to trial these enabling technologies to allow us to better understand the key drivers and the barriers to this new commercial concept.
I'd just like to point out that the Respond project we've looked at so far is existing customer database. These techniques can be applied to new connections also, which I do think there's potential a lot bigger market out there as well.
Just a question, so I'll just put that on. So what is the wider company appetite for the use of this Respond service with respect to new customer connections and potentially increasing fault levels?
Yeah, definitely. That's one of the objectives of the Respond project. I have personally been contacted by a lot of external connection people wishing to use some of these techniques. But as the project is only a trial at this stage, we're not really prepared to use it. We need to build the safety cases. But personally, I do see there is an appetite out there to reduce the fault level on network for new connections, for reinforcement connections. So definitely think it is a market we're interested in. But unfortunately, with it being a trial, it's very hard to sort of engage with them at this stage because they're after permanent connections.
The next question. I believe that you're validating fault levels at some sites. Have you found any sites where the fault level model needs refining?
I wouldn't say markedly at the moment. There are some differences. We've been using the Outram device, which is a very well used piece of equipment which can give you upstream and downstream fault level contributions, and it's been installed at a number of sites now, quite all the sites it's been round at least once. There may be some sort of alterations we need to do, or look at the differences between, for example, the tool we use normally, which is IPSA for the transmission system, and we use DINIS for the distribution system. So there's some interesting things come up. It's a bit early to sort of report them all at this stage because we need to understand it ourselves first. But yeah, some things have come up. In terms of fault level, one of the things that's interesting about Respond is that it doesn't define fault level, but certainly fault contribution from upstream the transformers. Because of the way we've done Respond at the 11 kV sites, we're summating the two primary transformer currents, and that's already come up with some interesting results. One of the interesting results is the fact that we've had, at Atherton Town Centre, we've had 3 face-to-face events. They've been face-to-face-to-earth events, but nonetheless, 3 events which was much more than we expected. And I think the reason this has happened is because normally we're using sort of fairly standard static 1980s relays, MCGGs at that site, and it's not being recorded as a face-to-face event because they're quite simple relays. So that's probably one of the biggest learning points we've had, is that we're probably getting more face-to-face events on our network than we thought. So it's not quite a fault level issue as such, but certainly a fault contribution issue.
Okay, so that completes all the questions you currently have on the webinar.
Okay, thank you all very much for attending. If you could spend a minute to fill in the poll that you'll see at the end of the webinar, that would be much appreciated before you disconnect.